Today we want to look at exponential functions. So our goal here is to define what is an exponential function and then kind of how we can use them and what they look like and all the kind of properties of them. And then as we go throughout this chapter, we'll look at more and more applications of exponential functions. So for today, we're just kind of defining what they are, what they look like, and what their properties are. Before we do that, though, I want to go back and review just some of the properties of exponents. We've seen these already. If you remember, we've talked about things, how if you multiply two things, you add your exponents, how you divide, you subtract your exponents, power to a power, you multiply, negative exponent, you think fraction. So these are all properties that we've already seen. So we're going to do a few problems just to kind of refresh our memories because we're going to be using these a lot in this chapter because we're dealing with exponential functions. Exponents are important. So just to review, if we have these two multiplied together, 2ab cubed times 5a squared b to the fifth. Our numbers, 2 and 5, we just multiply, gives us 10. For multiplying our bases, a, we have a to the first and a squared, 1 plus 2 is a cubed. And then finally, b cubed, b to the fifth, 3 plus 5 is 8. So we have the same base, we add our exponents. Now, if we are dividing, we subtract. So I have u to the 2 minus a negative 1. So if I write that 2 minus a negative 1. And then v, negative 2 minus 3. Well, minus a negative is a plus. So 2 minus a negative 1 is a 3. V, negative 2 minus 3 is a negative 5. And if I write that with positive exponents, that's u cubed over v to the fifth. Now, if I have a fraction raised to a negative exponent, I first am going to take the x and a power to a power I multiply and I get negative 6. 2 to the negative exponent is a negative 3. Now, negative exponent on the top goes to the bottom and becomes positive. Negative exponent on the bottom goes to the top and becomes positive. And then finally, 2 cubed is 8, x to the 6th. So let's kind of review some of the properties that we've already looked at with exponents. We've also talked about rational exponents, how something to the 1/2 power is the same as the square root of 4. The 1/3 power is the same as the cube root. The 1/5 power is the same as the 5th root. And those are all 2. Not every answer is 2. If we have 4 to the 3/2, this is the square root of 4 cubed, which is the square root of 64, which is 8. This is the 5th root of 32 squared. However, I don't know what 32 squared is, so I can write this as a 5th root of 32 squared. And the 5th root of 32 is 2. 2 squared is 4. So many times, putting that exponent on the top, on the outside of the root. For example here, cube root of 27 squared is 3 squared, or 9. And we've done these before. I think we actually used these same slides earlier when we just kind of started the year talking about exponents. We skipped those. We also talked about the difference between this and how if you have a multiplication, I can take 4 squared times 3 squared, and I can get the same answer. In this case, 144. However, if I have 4 plus 3, I cannot say 4 squared plus 3 squared. 16 plus 9 is not the same as 7 squared. I can't do that. So if we look at the difference here, if I have 2 to the negative 1, x negative 3, negative 1 as I multiply is 3. I get x cubed, negative exponent on the top, goes to the bottom. However, if I have a plus sign in the middle, I now need to simplify this fraction. I need to get common denominators, simplify this down into a single fraction, and now if I have to the 1 to the negative first, I can just flip the whole fraction and get my answer. So you can see, much more difficult with a plus sign than a multiplication sign. Be careful to notice the difference. The biggest problem is many times with the plus, people want to treat it the same because it's so much easier. It's much different. All right, we want to talk about exponential functions here. This is really what we're want to look at in this section. And exponential functions are very different than anything else we've looked at. Because, look where the x is. The x, the variable, is in the exponent. If you think of everything else we've looked at, let me just kind of here. We've talked about things like x cubed plus 3x squared minus 7x plus 1. Those are like polynomials. We've talked about things like 4x plus 1 over x minus 2. We've talked about all those kind of things. We've even talked about things like the square root of x, which would be x to the 1/2. But notice in all of those kind of problems we've looked at to this point, and most of what you've looked at to this point in all the algebra classes you've taken, you have had x, a variable, raised to a number. Now we have some number, b, raised to the x. And that's going to change how we do things. It's going to make it much harder when we try to solve for x, when we try to find x. It's much more difficult. Now, a couple things here. One, a can't be 0. B can't be 0, because if there's 0, the whole thing's 0. B has to be positive. If it's negative, you have that whole negative exponent or negative number things that causes problems. Also, B can't be 1, just for the simple fact that'd be boring. Okay. B is called our base. Okay. A is the constant, is our initial value. That will make sense here in a second. So the big thing is this B, when we talk about the base of our exponential function, that's B. Okay. Now, to think about this exponential function a little bit, let's look at some numbers. Let's evaluate. What is 2 to the 0? Well, that's just 1. Anything to the 0 power is 1. Go back to our properties from the beginning. That was one of our properties. 2 to the first is 2. 2 squared is 4. 2 cubed is 8. 2 to the fourth is 16. 2 to the negative 1, that's 1 over, is 1/2. 2 to the negative 2 is 1/4. 2 to the negative 3 is 1/8. Now, as you look at these numbers, I want you to think about something. Where do these fit in? Where is 2 to the 3/2? That's 2 to the 1.5. It's going to be in here somewhere between 2 and 4, but what? What about 2 to the pi? That's going to be in here, 3.14. But what's that equal? Now, you may say, well, let's just go to the calculator. And I can take 2 to the 3/2 and get that. Or I could take 2 to the pi. Messed it up. Let's try it again. back. 2 to the 3 halves. 2 to the pi. And you can see 2.8 is between 2 and 4. 8.82 is between 8 and 16. So it works. But how do we find these? Okay, that's where the exponential function comes in. We can put any number in for x. It doesn't have to be whole numbers. We can put in any decimal, any fraction, any irrational number like pi, and raise it to an exponent. Now, many times we're going to need a calculator to help us evaluate that because we can't do 2 to the pi by hand. So, our exponential function, though, would be 2 to the x. 2 is our base. So if I want to find f of 4, that's 2 to the 4th. That's 16. F of negative 3, 2 to the negative 3. Negative exponent, that's 1 over 2 cubed, or 1/8. 2 to the 1/2 for f of 1/2. We're going to think that's just the square root of 2. Or it will be 1.414 decimals. 2 to the pi. I'm just plugging pi in for x. And that was 8.825. So an exponential function, our variable is just in our exponent, which is new. It's different. We've got to be more careful. So let's find the exponential function that has these properties. F of 0 is 4, f of 1 is 12. Now we know our exponential function is f of x is a times b to the x. Notice a is not raised to the exponent, just b. So we want to use these two pieces of information that were given to find a and b. Well, if f of 0, if we plug that in, that's going to be a times b to the 0. We know that equals 4. But anything to the 0 power is just 1. So this a is 4. That is why, back here, they said a is the initial value. The value when x is 0. Because anything to the 0 goes away, so a is just your initial value. A is the value when x is 0. Now I got to find b. Well, I have f of 1 equals 12. Well, I know a is 4, so plug in a is 4, and I get b is 3. So my exponential function here is 4 times 3 to the x. You may even want to put parentheses around that so we don't think of it as 12x. Completely different thing. You can't combine those 3 and the 4. So there's my exponential function that goes through those points. Now let's talk about the graph of these functions. Now we've already looked at these a little bit with our parent functions. If our base, our b, is greater than 1, let's say like our 2 to the x, we could graph this and graph 2 to the x. We looked at this last week on the review. We get a graph that looks like that. So it goes through the point 1 and curves up like that. And it probably levels off here more than didn't draw it very good. But you can see that's what it looks like. Now, what happens when I have a number less than 1? Now, let's go on to the next page here and we'll come back. Let's say I have a number less than 1. This is my b. This is my base. Now, let's do a little work here. We know that 1/2 is the same as 2 to the negative 1, right? Because here it's to the first, you can flip it to the top and it becomes a negative. Now, our properties of exponents say when you have a power to power, you multiply. This is 2 to the negative x. Now, from the last slide, we know that 2 to the x looks like this. Think back to parent functions. Negative inside the function. Does that flip it over the x or over the y? If it's inside the function, it flips it over our y until we get a graph that looks like that. So when you think of something like a 1/2, it's just flipped over the y, because really you can simplify it to just a negative. So over here, the graph just looks like that. All of these go through the point 1, 0, when it's just b. If there was an a in front, then this would be a. When it's just a b, it's just 1. Now, we have one special function, and this is e to the x. And this is something that people just struggle with. I give you a little idea of where e comes from. It'll make more sense going on. It comes from this formula here. And as x gets bigger and bigger and bigger, you get closer and closer to e. So it's on your calculator. We will use it a lot. Second natural log. And if I take e to the first, I get 2.718281828, so forth. Here you can see, here's more decimal places. This is an irrational number like pi. Never repeats, never stops. And I show you more decimal places, because on the calculator, it kind of looks like it repeats. 1828, 1828. But here you can see that's really not true. Okay. 1828 gets it's a little different. Okay. So we will talk more about this. I just want to introduce this. This is called the natural exponential function. It's a special case where your base is this e value, this 2.7 value. We just kind of seem to pull it out of thin air right now. It will come back up later in the rest of this chapter. Now, one of the advantages of e is we can convert almost anything to base e. Instead of having 2 to the x, I can have it e as 2 to the kx, when k is this crazy number, and 3x, I can have it as e when k is this number. That will help us as we do application problems, because everything will be written in base e. So let's look at an example. The number of bacteria in a petri dish cultured after T hours is given by this formula. The bacteria is 100 e to the 0.693 t. So what's the initial number of bacteria? Well, initial is when t is 0. So if we put 0 in, that's 100 e 0.6930. But as we've said before, anything to the 0 power is 1, so we just get 100. So that's the number of bacteria that's initially present. Remember, it's just our A, where in this case our base is E. Now, how many bacteria are present after 6 hours? Well, I just want to plug in 6. This is 100 E 0.693 times 6. Now, there is no way for us to do that by hand. This is all calculate. Okay. So 100 to the E, 0.693 times 6. If you don't have a calculator like mine, you may have to be careful with the parentheses as you put this in. So we get 6394.35. Now, obviously we cannot have a partial bacteria, so I'm going to round this up to 6395. Okay. We're not going to round closest, we'll always just round up. Okay. Now, how long until the approximately 10,000 are present? So I have my formula, and now notice what I'm trying to find. The number of bacteria equals 10,000. And I want to find T. Now, at this point, we have no way of getting our T down from the exponent. Nothing we can do. This is why on tonight's homework, it's going to say approximately. Because what we're going to do is we're just going to approximate. We're going to guess and check to try to get close. So I'm going to change this to 9. See what I get. Okay, it was a little too big. Let's go back. Try 7. Okay, still too big. Second enter just takes me back. I can go back area. Let's go getting closer. Let's go 6.6, and I'm just picking that because it's between 6 and 7. I'm getting closer, a little bit bigger, and we just want to guess and check until we get close. Let's try 6.8. Okay, too big. Oop. Got that in wrong. It's pretty close to 6.6. So I'm going to try, instead of going 6.7, I'm going to try 6.65. Oh, now I'm very close. Let's see, a little bit less. Let's go 6.64. A little bit more. 6.645. Just kind of trying to get how close I can get, and I'm within 2. We're going to go with that. 6.645. At this point, there's no way to find that exactly. There will be, give us time. But for now, we're just doing guess and check on the calculator. All right. That is it for the video. We will work on the problems on the homework on exponential functions tomorrow in class.